Okay, well, welcome back. I hope everyone enjoyed the first coffee break. Just a quick reminder, look for the code words throughout the day's programming to redeem them for points using the gamification buttons on the event page. Add up your points, claim your prizes. It's going to be first come, first serve. So we'll get back to the festival programming. And up next, we have Josh Lewis. Josh is going to be speaking to us today about optimizing HVAC systems for a healthy environment. A quick intro for Josh. If you don't know him, he's an engineering manager at Hrv Energy Group. Hrv is an energy advisory firm and specialty contractor providing smart building optimization solutions. Hrv ensures buildings function more intuitively and more efficiently, creating energy earning and carbon reduction opportunities, while at the same time fostering a positive impact on occupancy, quality of life, and overall environment. So wonderful. Welcome, Josh. Really look forward to your presentation. Over to you.
Thanks, Mike. Much appreciated. So I'd like to express my gratitude to Sustainable Buildings Canada for this opportunity, as well as my appreciation to all of the attendees online with us today. So back in March of this year, when I was discussing the outline of this presentation with the organizing committee, there was quite a bit of hope that by October, COVID-19 would be on significant decline, and the emphasis of my presentation should be on the need to focus on the health of our buildings in general and be prepared for future shocks. But through a combination of factors such as the Delta variant, as well as vaccination rates that have lagged behind what is needed for herd immunity, we are still in the throes of this current pandemic, much to everyone's dismay. When COVID-19 became a pandemic in 2020, there was an immediate realization that the risk of transmission within buildings was likely very high due to the aerosolization of virus particles. This forced building owners and operators to quickly implement strategies to improve indoor air quality and reduce the risk of disease transmission. However, many of the common strategies to improve indoor air quality can lead us down a path of reducing the energy efficiency and increasing the carbon emissions of our buildings. But for both our health and the future of the planet, we must achieve a balance between efficiency, air quality, and comfort. However, the light at the end of the tunnel is getting closer. And within the just society we live in, our shared morals dictate that we cannot put a price on the health and safety of any individual. It is a supreme right that must be protected. To make our commitments, we must ensure that all heating, ventilation, and air conditioning systems, also known as HVAC systems, are optimized for a healthy environment, which means that they can simultaneously provide the best indoor air quality possible, while also being energy efficient and reducing or eliminating greenhouse gas emissions. Due to deeper and deeper encroachment on nature by humans each year, as well as the globally connected world we have built, it is likely this pandemic is not the last in our lifetime. Combined with the ongoing threat of more typical indoor air quality issues such as stale air, particulates, volatile organic compounds, also known as VOCs, mold, and other contaminants, our long-term health can be impacted without the right strategies and operations in place in our buildings. When talking about the specifics of COVID-19 transmission, the ranked risk of vectors is as follows. Number 1, person to person. Number 2, airborne particles, and number 3, contaminated surfaces. These vectors are certainly not unique to the current pandemic, and more commonly, they are also applied to seasonal flus and colds. While it is impossible to reduce the risk of disease spread to zero, as a society, we have implemented several specific actions to address each vector. For person-to-person transmission, we are combating it through masks, social distancing, barriers, and small bubbles of interaction, and working from home. Contaminated surfaces are being addressed through cleaning, antimicrobial surfaces and coatings, gloves, and hand washing. But today, the focus is on airborne particles. While quality masks can offer some protection against contaminated indoor air, ultimately, we need to ensure our HVAC systems within our buildings are designed, installed, and commissioned to maximize indoor air quality in order to reduce transmission risk. But at the same time, we have other competing priorities. Improving energy efficiency and reducing greenhouse gas emissions in order to combat climate change. I will be honest, up until this pandemic, the majority of energy conservation measures that were being implemented on HVAC systems were likely having a negative impact on indoor air quality. This is no one's fault. It's simply the end result of trying to achieve energy efficiency targets using traditional methods. I firmly believe that most people, including myself, fall every day into what I call the indoor air quality or IAQ trap. What is this trap? Well, if we walk into a building and it feels comfortable and we do not smell anything strange or offensive, then subconsciously our brain does not register any concerns about the health of the building. However, many of studies have shown that nothing could be further from the truth. The fact is, our senses are not finely tuned enough to detect most contaminants in the air that can impact our health and well-being. So what are the key operational parameters that we must ensure our HVAC systems are set up to do and do well so that we can achieve a high level of indoor air quality? Well, they are filtration, dilution, purification, and humidity. The details on these four parameters are the focus of this presentation. But before we jump into those details, let's lay some groundwork of what can happen if one or more of these parameters has not been effectively implemented. In the early days of the pandemic in China, specifically January 2020, there was an outbreak associated with an air conditioning system in a restaurant. As you can see on the diagram, patient 0 was sitting at a table on one side of the dining room. On the wall, there was a split system air conditioning unit, which to the best of my knowledge had ineffective filtration, no dilution, as this type of setup typically does not include the mixing of any outdoor air, and there was no purification or humidity. Over the course of the meal, patient 0 managed to infect at least 8 other people on their side of the dining room. Yet, people at the other nearby tables did not get infected. The working theory that is being researched is that the AC unit created a recirculating air pattern around the tables near the wall, which distributed the aerosolized virus particles in a structured and measurable way. While the final conclusions for this outbreak have not yet been published, many other studies and accounts strongly suggest the root cause identified here is valid. And keep in mind, this is long before even the more transmissible Delta variant was a concern. We need to ensure that our HVAC systems are optimized for a healthy environment. Does that mean safety is number one? Yes. But the larger picture also forces us to include other goals in that assessment, such as reducing risk and liability, maintaining comfort, and managing and conserving energy use. It is important to note that in almost all cases, there is no single solution that can be applied to HVAC systems to achieve these goals. Only a logical combination of changes and upgrades are likely to be successful. There are key considerations that we must reflect upon when looking at the details of how a typical energy conservation measures for HVAC systems are likely having a negative impact on indoor air quality. Efficiency, first and foremost, is achieved as a result of tight control of temperature set points in our buildings, both in the occupied and unoccupied or setback states. This measure is not known to have any negative air quality impacts. However, the next four are problem areas. They include only having basic filtration, only operating fans when required, minimizing fresh air, and not controlling humidity levels, especially in the wintertime. If we want to benchmark buildings that have above average indoor air quality, we need to look no farther than hospitals and other healthcare facilities. These types of facilities are mandated by codes and regulations to have HVAC systems that move large, constant volumes of air, bringing in a high percentage of fresh air into the building, and have tight filtration and humidity control. Why? Well, because years and years of research and experience has shown the healthcare sector that this type of HVAC configuration greatly reduces the risk of healthcare-acquired infections, such as pneumonia, staph, MRSA, sepsis, among others. However, virtually no other type of buildings are designed and constructed as healthcare facilities are, and if they were, their baseline energy consumption would be very high. The indoor air quality solutions for typical buildings must be different. COVID-19 has been a trigger to force us to rethink about what HVAC systems should do. Allowing ourselves to fall into the IAQ trap is no longer acceptable. We need to effectively remove contaminants out of the air through a proper mix of filtration, dilution, purification, and humidity. The benefits will extend well beyond the current situation we find ourselves in, including reducing the risk of spread of seasonal flus, colds, and other airborne pathogens, while also reducing the concentrations of allergens as well as VOCs that are inevitably generated due to the materials we use for construction inside buildings. Filtration is the first key operational parameter that must be optimized. Filters are present in virtually all HVAC systems, and they're designed to trap various contaminants in their collectors. Their performance is critical, as they must be capable of cleaning the air as it's passing by. Minimum efficiency reporting value, commonly known as MERV, is a measurement scale designed in 1987 by the American Society of Heating, Refrigeration, and Air Conditioning Engineers, also known as ASHRAE, to report the effectiveness of air filters in more details than other ratings. There are three key questions that I challenge building operators to ask themselves. Do you know your current filter performance levels? Do you know your current filter conditions? And what is your strategy for changing filters? If there are not clear answers to each of these questions, there is a potential that the indoor air quality is not optimal in that building. Now, according to ASHRAE, filters with a MERV 13 rating are the minimum recommended for the effective capture of COVID-19, and they are also effective against a large range of other types of viruses, bacteria, and other contaminants. However, this is an upgrade from the baseline state of most HVAC systems, which in the past have typically been equipped with pleated filters with a MERV 7 rating, or even worse, media-style filters, which only capture large debris and thus are practically useless against most contaminants. Thankfully, many pieces of HVAC equipment can utilize MERV 13 rated filters by simply swapping them out, negating the need for any systematic changes. But this change comes at a cost. Filters with higher MERV ratings need to be changed more often, as they will naturally capture more contaminants in a shorter period of time. There's also the potential need for the system fan to work harder to pull air through the filters, creating an uptick in electricity usage. The impact of both of these concerns can be minimized by using a measurement, specifically the differential pressure drop across the filter. The amount of pressure lost across the filter provides a clear indication of how dirty the filter is, and also how much impact it's having on the amount of energy the fan is using to move the air. The most energy efficient, cost-effective, and environmentally sustainable way to decide when to change a filter is to measure and monitor the differential pressure across it, then swap it out when it hits the manufacturer's recommended pressure value. There has been a lot of talk since the pandemic started about HEPA filters. HEPA, also known as high efficiency particulate absorbing filter or high efficiency particulate arrestance filter, depending on where you're from, have equivalent MERV ratings between 17 to 20. Now, this type of filter has typically been used in healthcare facilities and other buildings that are very sensitive to indoor air quality, including laboratories and manufacturing facilities with clean rooms. They are definitely more effective at trapping contaminants, but due to their inherent tightness, the differential pressure drop across a HEPA filter is quite high, even when they're new. Therefore, most HVAC equipment cannot accept HEPA filters as they were not designed for it, and if installed, they would cause an unacceptable decrease in system airflow while simultaneously increasing fan electricity usage by a significant percentage. Another more fundamental problem with HEPA filters as a standalone solution is that while there's no doubt they capture the vast majority of contaminants, the method by which they do that function requires the contaminants to reach the filter. If the rate of air circulation within the interior of the building is too low, then the ability of the filters to quickly clean the air will be hampered. A real-life example of this are the portable filter carts with HEPA that have been installed in many schools in Ontario in order to respond to COVID-19. While the HEPA filter will capture the virus under most circumstances, the contaminated air has to travel from wherever it was generated in the classroom, say by a student sneezing, to the cart. If the filter cart does not have a large enough fan, then the effective air circulation rate may be too low to reduce the transmission risk significantly. ASHRAE recommends that if relying on filtration to clean air, then at a minimum, all of the air within the volumetric space should be filtered at least 4 times per hour, but ideally at 6 times per hour. There is a non-conventional filtration option available that can provide both high filtration and superior energy performance. Electrostatic air filters separate themselves from pleated filters by using electricity to catch dust, pollen, and other airborne particles. They can achieve a high MERV rating with a low amount of differential pressure, as they have large openings which rely on the electrical charge to capture and hold the airborne contaminants. While electrostatic filters have a higher upfront cost, they typically have a lower cost of ownership over their life cycle because when dirty, they only require the filter media to be washed, not replaced. While they have not typically been a standard in HVAC systems, many off-the-shelf retrofit kits are available. However, if considering going this direction, the whole picture must be evaluated, including the fact that monthly washing of the filters will be needed, a HEPA level of performance will likely not be achieved, and some electrostatic filters can generate ozone as a byproduct, which is an indoor air pollutant that is not desired. In summary, filtration is the first key operational parameter that must be optimized to create a healthy environment. Ensure that the installed filters have the right performance level, that there is a clearly defined strategy to know the current filter condition and when to change them, and that the HVAC system air circulation rates are appropriate for the filters to be effective. The next key operational parameter is dilution. Dilution can be further broken down into two major strategies: keep air moving and the introduction of fresh air into the building. Let's start with keep air moving. So keeping air moving through buildings is key for a healthy environment. Stale, stagnant air can expose the occupants of a building to several risks, including both airborne contaminants of all kinds, high CO2 levels due to the breathing process of people within the space, and also odors that act as irritants. And as discussed previously, good air circulation is critical for filters to perform properly. Also, it's not just about improving airflow. Some buildings, especially schools, were not even designed and constructed with mechanical ventilation systems. For example, in Toronto, Ontario, at least 99 public schools have no mechanical system and rely on windows alone for air circulation. And typically they have hot water radiators for heating in the winter. Well, that kind of design has not been acceptable within the building code for decades. Our stock of school buildings in Ontario is quite aged, averaging on 39.4 years old, with many much older than that, including some even from the late 1800s. These older buildings have likely always had less than perfect indoor air quality, which the current pandemic has now exposed. Specific actions that have been implemented to keep air moving usually start with ensuring that the HVAC system is running in fan-on mode, meaning that during the hours of the day when the building is occupied, the fans are running constantly to push air in and around the building. You might ask yourself, isn't that how HVAC systems are supposed to work? Well, not necessarily. If you think about the furnace most of us have in our homes, often it is set to fan auto mode, which means that the fan only turns on when there is a call for heating or cooling. If the temperature set point has been satisfied, then the fan is stopped, as is the air circulation. While this is energy efficient, it has a negative impact on indoor air quality. The typical way that the operation of the fan is changed and tracked is through Hvac controls, also known as building automation systems. By installing, upgrading, or retrocommissioning the controls, the fan operation can be set up to provide the air circulation needed when the building is occupied, while reducing the energy waste by turning the fans off during unoccupied periods. Next, if the fan is it running at its maximum capacity? To improve the energy efficiency of HVAC systems, they've often been designed or upgraded to include variable speed drives, also known as variable frequency drives. These electronic systems allow for the fan speed to be dynamically changed through either manual or automatic intervention. In most cases, the drives have been set up on a schedule and configured with a limited maximum fan speed in order to reduce energy consumption and carbon emissions. Unfortunately, during a pandemic, this strategy must be altered. Instead, we want to maximize fan speed, which maximizes air circulation of the existing system. When making this change, the original settings should be recorded and saved so that the parameters can be reset to their existing values once the situation which demands that we prioritize indoor air quality over energy efficiency has passed. Lastly, for keeping air moving, if the fan is on and is set to its maximum speed, there is one more common part of HVAC systems that we must consider in order to keep the air moving effectively. It's not really well known that virtually all ductwork systems leak, which impacts both indoor air quality and energy efficiency. ASHRAE states that 75% of commercial duct systems leak between 10 to 25% in their duct design manual, with reports from the field that real-world ductwork leakage rates are typically about 10% higher, ranging from 20% to 35%. So why is there so much leakage? Well, the traditional methods of sealing ductwork from the outside with mastic, tape, and caulking are not perfect. Oftentimes, sealing is missed on hard-to-reach areas or lengthwise seams that seem to have very little leakage in a small section, but cumulatively add up to a significant amount of leakage over hundreds of linear feet of ductwork. Any air leaking from ductwork before it reaches the occupied areas of the building reduces air circulation rates and wastes energy, as the areas it is leaking into, including ceilings, shafts, mechanical spaces, are not designed for nor intended to be ventilated. If duct leakage is reduced, there will be immediately more air circulation in the space that people occupy, improving indoor air quality and reducing the risk of disease transmission. Ductwork can also be sealed tighter in new and existing buildings through various methods, including the traditional method of using mastic tape and caulking with an extra level of attention to detail, and also through new technology now available to seal ductwork for the inside using a pressurized and spray system. Regardless of which method is selected, ductwork sealing is one of the only strategies that can improve indoor air quality while also saving energy usage over the long term, creating the potential for a win-win scenario. To close out dilution, we also need to discuss the introduction of fresh air into buildings. Replacing a percentage of the interior air with fresh outdoor air helps dilute and expel contaminants, which may be causing indoor air quality issues. If we brought 100% fresh air into a building all of the time, the indoor air quality would be expected to be quite good. However, from an energy efficiency point of view, the amount of energy needed to run at 100% would be staggering for most buildings compared to their baseline. It has become more common in recent times for buildings to implement demand control ventilation, which is a building automation technology that continuously measures the concentration of CO2 in the space, and based on that level, decides when to bring fresh air into the building. While this technology is mature and proven to have a large beneficial impact to energy efficiency, it can reduce indoor air quality because there can often be long stretches of hours or even days where no fresh air is being introduced. During this current pandemic, it has been highly recommended by Hrv and others to disable demand control ventilation systems, especially during occupied hours, in order to bring a guaranteed volume of fresh air into the building to combat aerosolized disease spread. The other related strategy for using fresh air strategically to create a healthy environment is called flushing, which involves setting up the HVAC system to bring in copious amounts of fresh air during at a defined time, such as, for 2 continuous hours after the building becomes unoccupied every day. This can be very effective at removing contaminants without necessarily having a very large impact on energy efficiency. Now, the inherent loss of energy efficiency when bringing fresh air into a building can be mitigated if the HVAC systems in the buildings recover heat, or both heating and cooling, from the inside air being exhausted to make room for the incoming fresh air. This is typically accomplished with systems that perform heat recovery ventilation, also known as an HRV, or energy recovery ventilation, also known as an ERV. HRV and ERV systems come in many forms and utilize different types of heat exchange mechanisms, from metallic cores to wheels to semi-permeable membranes, and even paper. Their overall purpose is to capture the energy from the air leaving the building, both in the form of temperature, also known as sensible energy, and humidity, also known as latent energy, and then give up that energy to the air coming into the building, with typical equipment efficiencies ranging between 50 to 90% recovery. By using these systems, more fresh air can be brought into the building with much less of an impact to total energy usage. This has a positive impact on both the indoor and outdoor environments, and can go a long way to improving indoor air quality without creating a massive spike in energy use. While there are a lot of good practical actions to achieve a healthy environment contained within filtration and dilution, there are still 2 more key operational parameters, with the next one being purification. Purification in this case is defined as systems which clean the air of contaminants, excluding filters. So the most common type of air purification systems utilize ultraviolet light to kill biological contaminants in the air, including viruses and bacteria. Ultraviolet systems are not a new technology, but prior to the current pandemic, were mostly utilized in hospitals and food processing facilities. UV light is electromagnetic radiation with a wavelength shorter than that of visible light, but longer than X-rays. It covers the wavelength from about 100 to 400 nanometers. For disinfection, aka purification, the process typically uses wavelengths in the UVC range from 240 to 280 nanometers. By properly installing UV lights into the ductwork, the air passing by them can have any biologics within it inactivated due to exposure to the rays. For safety, it is critical that the lights are completely contained, as direct exposure to their output can have harmful impacts to anything living, including but not limited to the injury of sensitive cells contained within the eyes, creating the potential for blindness, which we certainly want to avoid. Many UV systems use this described direct exposure approach to purify the air, which is also known as a form of passive air purification, meaning that any biological contaminant must pass by or through the purification system to get the air clean. Filters also fall into this category of passive air purification. The other types of system, known as active air purification, work differently. They typically use UV light or an electrical discharge to drive a chemical reaction which can produce active ions within the airstream, such as hydroperoxide, ozone, and other types of ions which flow with the air into all areas serviced by the system, directly attacking contaminants through the surface space, both in the air and on surfaces. Active air purification, when implemented properly and safely, has major advantages over passive systems. They essentially fill the building with beneficial ions, turning the air itself into a protective blanket. When a virus is expelled from a person's body due to a sneeze in a building with an active system, the contaminants in the air are attacked immediately as they move away from the person. While active purification systems can be extremely beneficial in our efforts to improve indoor air quality, care and caution must be taken to select the right technology. Since COVID-19 has become a pandemic, there's also been an associated infodemic regarding air purification, which is described as information including false or misleading information in digital and physical environments during a disease outbreak. Without getting deep into all of the available technologies on the market, there are a few key questions that should be considered when evaluating and purchasing an active air purification system, including: does the system produce multiple beneficial effects? Is the system proven effective in both the lab and the real world? What kind of third-party certifications does the system have? Does the system produce ozone or radicals? This is important because both of these, while having a purification effect, are also indoor air contaminants that we probably don't want to breathe. And last but not least, does the system utilize LED technology? If so, it will likely use less energy and have a longer in-service life. Air purification systems are not part of any regular building code, nor are they expected to be in the short or medium term. However, the right system can produce a powerful yet safe purification effect in buildings, which can not only improve indoor air quality, but also allow for the adjustment to other operational parameters, such as safely lowering the amount of fresh air that needs to be introduced, which will improve energy efficiency and also lower carbon emissions, assuming you're using gas to heat, which we primarily do. The last key operational parameter for a healthy environment is humidity. As you can see on the graph, many years of research has clearly shown that the control of humidity levels in buildings is critical to maximizing indoor air quality. Whether talking about bacteria, viruses, fungi, mites, or other contaminants, they are all minimized if the relative humidity is between 40 and 60%. If possible, controlling to a tighter range of 40 to 50% indoor air humidity will also keep the mold growth at very low levels. Corollary to this, keeping humidity under control has also been shown to have many other indirect benefits, including reduced absenteeism, improved occupant mood, and increased productivity, all of which are likely the result of people within the building being healthier. In the past, the most common types of buildings to have year-round humidity control, other than healthcare facilities, were those containing Class A or top-tier office space, but typically not other facilities. In our buildings in Canada, we typically do a good job of maintaining indoor humidity levels in the optimum range in the summertime because our air conditioning systems are designed primarily to dehumidify the air, as that is the largest portion of the cooling load, which has to be addressed in order for the cooling system to be effective in our climate. But in the winter, the air inside the vast majority of buildings will typically have low humidity levels, usually between 10 to 30%. This is a directly result of the condition that we set ourselves up for. With the outdoor air in the wintertime, it's cold and dry. And when it's brought into the building, either through the HVAC system or by infiltration through the building envelope, it's heated up. which makes it even drier in relative terms. From personal experience, I have seen the humidity level in an apartment building in the wintertime here in Ontario as low as 7%, which is bone dry. We might as well be in the desert. But that is a direct result of the building doing what it was designed to do, bringing in large volumes of makeup air from indoors, heating it up to 21 degrees Celsius and dumping into the hallways. No other result should be expected at that point. The solution to wintertime humidity issues are pretty straightforward, but it does have a penalty in terms of cost and energy. Humidity injection systems must be installed into HVAC systems. In the past, these systems were typically steam-based, but those are now considered obsolete due to their high cost and extensive maintenance requirements, also excessive energy use, except in hospitals where they're still required by code. Newer humidity systems are typically based on either ultrasonic or high pressure spray technologies. Regardless of what type is chosen, there will be installation, energy, and maintenance costs associated with it that are above and beyond the requirements of the building code in order to create a healthy environment. But harkening back to a statement from the beginning of this presentation, in our just society, it is impossible to put a price on the health and well-being of any person. In summary, in order to optimize our HVAC systems for a healthy environment, there really is no silver bullet. Instead, there's a menu of complementary options which need to be weighed against each other, whether we are attempting to improve an existing building or design a new building. Filtration is key to ensure that contaminants are captured. Dilution, including keeping the air moving and introducing fresh air, ensure that the filtration is effective and that the air is changed over consistently. Purification adds a layer of protection by specifically targeting biologics, and humidity control is absolutely necessary for improving occupant health and well-being. While implementing every option will very likely result in superior indoor air quality, the reality of it is there is a simultaneous need to be energy and carbon efficient, which is not just about using less energy, but using the energy more efficiently for the job that we're trying to achieve. Once again, I would like to thank Sustainable Buildings Canada for this opportunity, as well as my appreciation to all of the online with us today. I trust that you found this session informative. I think we're going to open it up to Q&A right now, and I will also be online for the afternoon coffee break and speaker chat at 2:30 to discuss any further questions and comments regarding this session. Thank you for your time this morning.
Fantastic. Thanks so much, Josh. That's an excellent presentation. I'm an engineer and I still took away a lot, so really good stuff. A lot of questions were streaming in, so we have about 5-6 minutes to tackle some of those, so why don't we hop in. The first question is asking about the significance of the impact of contaminated surfaces compared to aerosolized, they're saying sprays, but I think perhaps particulate matter, in terms of potential for infection by ingestion of those contaminants and thinking COVID-19. The question goes on to say that perhaps there's an overemphasis on cleaning surfaces, perhaps because that's easier to control and to see. So I think the question is around that balance between surface contamination and aerosolized contamination.
Yeah, I believe our thinking in regards to, especially to COVID-19, has changed on that. So originally it seemed to be almost an even balance between aerosolized virus and virus contaminated on surfaces. But future, further research by people way smarter than me has kind of shown that the risk of surface contamination and transmission via that method is not nearly as high as it is with the aerosolization. COVID in particular seems to be a very, very aerosolized virus. The Delta variant is even more aerosolized. So whereas we were 50-50 before, I think now we need to be more maybe 80-20, maybe 85-15, definitely more heavily leaning on the HVAC systems and the aerosolized risk rather than the surface risk.
Yeah, I'd agree, Josh. The next question, is there an argument for 100% fresh air? And the question goes on to perhaps contextualize that a bit by saying, thinking about pre-tempering that incoming air. So I think, what are your thoughts on 100% fresh air systems?
100% fresh air systems are probably some of the safest systems that we could possibly build, install, and commission. The problem is that the energy and carbon efficiency of those systems traditionally is absolutely terrible. So if you're going that route, especially if you're going to do a major mechanical retrofit, 100% fresh air or close to it is more achievable these days, but you need to put in the proper heat recovery equipment to make sure that you don't blow your energy and carbon budget on that. And there are, without naming any manufacturers or anything like that, but there are equipment now, rooftop mounted equipment or mechanical room mounted equipment that can recover up to 90% of the exhaust air energy. So, you know, that's really starting to approach the physical limits of whatever we'll be able to achieve. So if you're recovering 90% of the energy, then going to 100% fresh air is not going to be a huge impact on your budget. To be perfectly honest, if you were taking a building from a standard rooftop configuration with 20% fresh air, which is typical if you're not doing demand control ventilation, and you put on a 90% heat recovery makeup, air handling unit, you might actually even reduce your energy while getting your energy load while getting the 100% fresh air at the same time and have a real win-win. Those systems aren't necessarily cheap, but we got to think long-term.
Yeah, I agree. Great answer. Next question regarding ionization filtration and the concern that it may produce ozone. I guess trying to understand, where is that risk balance point, and is that risk great enough that we should just look to other filtration methods?
So where the risk is introduced with ionized air purification systems that, you know, like I said, it's a very, very deep and wide market, and full of different vendors, technologies, and claims, some which stand up and some that don't. I think the key is to rely on UL standards. Don't rely on any information provided by the manufacturer unless they're referencing that their technology has been tested against UL standards. UL has two standards for air purification. One is low ozone and one is zero ozone. So if the manufacturer does not have at least the low ozone certification for any type of ionization system, stay away from it. It's not even worth evaluating in your matrix.
Yeah, very good advice, and thanks for sort of keeping it simple. That's great. Maybe time for one more question. A question about the systems that you described and various approaches. How does that tie into the well building standard? And maybe I'll expand that a little bit, but just in terms of healthy building standards in general.
I'll be perfectly honest. I'm not an expert on the well building standard per se, so I don't know exactly what is contained within it. But I would be fairly certain that it would give you points for maintaining indoor air quality. Now, indoor air quality is not a single measure, right? It is CO2 levels in the building, right? That's a very key consideration. It is also particulate levels, which are typically measured on a scale of PM 2.5 or PM 10. But it's also temperature. It's also humidity. So all of these parts and pieces go together. I would suspect that, if you logically implemented what I talked about today in a defined way, that I think you would get pretty close to where well and fit well and those other certification standards are leading you towards. Like I said, I think the biggest missed opportunities that we don't normally think about is really humidity. I don't think we do proper humidity control in the vast majority of buildings. In fact, I know we don't. I know even in our own office here, we suffer from that in the wintertime because that's what the system, again, was set up and designed to do. So we are actually strongly considering purchasing a small duct-mounted bolt-on humidifier for this winter and running a water line to it so that we can even maintain better humidity levels even in our office space. But certainly humidity, and then certainly the purification technologies, which again have been underrepresented in the market and really sector specific, that I think we now need to look for wider adoption in order to protect ourselves, not just today, but from future pandemics.
Yeah, good answer, Justin. Yeah, I think thinking about the building as a system and how all these pieces tie together. Yeah, your thoughts on humidity really got my wheels turning, and I agree. And you can see it in the questions. I think it's an underlooked at factor when we think about healthy, high performance buildings. And maybe for the better that the pandemic has shined some light on that and forced us to all think about it and hopefully do things a little bit differently going forward.
I'll be honest, Mike, this is something I say all the time. I don't think we'd be talking about indoor air quality if it wasn't for the pandemic. I think that was something that, especially in the energy efficiency world, that we ignored. Not through any malice. This is simply because, again, the IAQ trap. You know, does the temperature good and does it smell? There's no smells, and then we think the air quality is good in our building, but a lot of research shows that nothing further could be the truth. You know, nothing could be further from the truth.
May not be the case. Yeah, I agree. Well, there's other questions, but Josh, I think we're going to wrap it there. As Josh said, he's going to be available in the coffee chats throughout the day, and I know Josh from many other engagements, so I'm sure if you'd like to reach out to him, he'd be more than happy to chat with you anytime. So I want to thank you, Josh. Excellent talk. And I will remind once again, before you head over to your next speaker session, register for those continuing